Hello everybody. In this tutorial we're going to play a little bit more with blockMesh and we're going to learn how to make our own geometry, which is a little bit less trivial than just the cavity case. So we're going to have a geometry which is a T-junction, so it's going to have 4 different blocks in it. Okay, so let's open up our Ubuntu. So I've pinned to the toolbar here. In fact, I'm going to open up two Ubuntus because I'm going to use one to keep my blockMesh ticked open and the other one is going to run blockMesh. You don't have to do that, but it's just convenient. So on my search, if I hold shift and then left click, that'll open the second one, and I'm going to put that on the right. Great. So on both of them, I'm going to bring it to the run directory. And as you can see, cases from previous tutorials. So if I what I'm going to do is make a new mesh. I want it to be an OpenFOAM case again. So typically in OpenFOAM, if you're making a new case, you decide on what solver you're using, and then you'll copy a tutorial case for that solver, and then you will replace the mesh and update any settings. So you never create a case from scratch. You'll always be copying another model and editing it. So go foam, tutorials, tab, press escape, hold control, press E. That's not normally required on most terminals, but it's something to do with the particular version of Bash on this. Go back and backspace / tab. We'll see all the different tutorials. So we go incompressible, tab again. Oh, we're in the wrong place here. Yeah, tab again. So we have OpenFOAM. We're going to later use SimpleFOAM. There's PiezoFOAM, which is very similar to OpenFOAM, but it allows you to use turbulence models. So we go OpenFOAM, cavity, and we're going to copy that to the current directory, but we're going to rename it and we're going to call it T-junction. So our case is going to be called T-junction. So might as well open explorer.exe in the current directory as well, just so you can follow along. So here's our T-junction. It's just the cavity case, which I've renamed. However, we're going to change mesh, then we're going to change boundary conditions, and then we're going to run it. Okay, so in my left terminal over here, I'm going to use Emacs, or you can use whatever text editor you want to open up system blockMesh ticked. And then on the right hand side, we're going to run blockMesh. So let me get the right hand side directory to the right place. And so T-junction, ls, now we're in the right place. Okay, so let's look at the geometry we're going to create. So on the PDF slides you can download, you will, for tutorial 4, it explains the geometry we're going to look at. So the geometry looks like this. It's a 2D case. So we have a large pipe with a small pipe perpendicular connecting to it. And so we have one inlet here, a certain velocity coming in, and then we're going to have a higher velocity being injected into this main pipe, and the outlet's going to be over here. So it's different, you can see from the cavity case, which doesn't have any inlets or outlets. So how will we create this in blockMesh? Well, it'll look like this is one way to do it. So you can create it by making 4 blocks. So if you see this, there's one block here, another block there, another block there, and another block there. So the coordinates we're going to use, and based on the geometry shown here, you can see it's 2 by 2, this part, then 1, then 3, and then it's 2 along there. So we can define our origin anywhere, but I've decided to pick in the top left. So the way I've done the coordinates, if you look at the, and here's the origin, then you move 2 in this direction, 3, and then 3 more to 6. And you move up 2, back 2, back another 1, back another 2. And you can see you've 2 up to all these coordinates. And then the front plane, it doesn't matter the Z coordinate for the front plane for a 2D simulation in OpenFOAM, because the third direction is just the way OpenFOAM represents 2D cases. So I've just picked it to be 1. So all of these dimensions, I think I've said I'm giving them in millimeters. Yeah, dimensions in millimeters. So what I'm going to do is in my convert to millimeters, you can see I've given the coordinates here. So I'm going to give everything in millimeters, and then if you set this global scale at the top convert to meters, that will multiply all these millimeters by 1e-3, so that will make them into meters. So then for the points, I can just remove all these, and then I basically just start adding the points from the geometry here. So 0, 0, 0, etc., etc. So the only thing is the order. I have to decide some order to go through them. So you can list the points in any order. It'll just affect how you define your blocks later. So this is the order I picked. I say this is point 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you see I went around the outside, and then I followed the same order, starting at 10 here. So where the original 0 is, I just go to the front plane of that and go 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So then the order of the coordinates I have to give them as this one first, this one, in that order. So I can type all those out, but I've given them here, so I'll just copy and paste them. I mean, that's probably easier, assuming my paste will actually work here. It may not work, in which case I will have to paste them. Oh, it did work, yeah. So let me just delete this. So you can see the order here, I put a comment in just to make it easier to follow. So 0 up to 19. So then in terms of the blocks, if we look at here how we've structured this, this I'm going to define as block 0. So it doesn't matter which one is block 1, 2, or 3, 4. It's just however you define it. So block 0 are these 8 points. Block 1 here, you can see share 4 points with block 0 and block 2. And this is block 2 and this is block 3. So 4 blocks. So the order in which the blocks are, the points for the blocks are specified. We didn't touch on that in the previous tutorial. We talked about patches, but there's a similar right-hand rule idea. So to define one of these blocks, you can see previously for cavity case, it's just 0, 1, 2, 3, 4, 5, 6, 7. And then it's at 20 by 20 cells. So how do you define the order of these blocks? Well, you start at any one point, and then you pick a plane and you go around that plane using actually the left-hand rule. So it's the right-hand rule if your thumb is pointing into the block. So this is different from the patches. So if you imagine we're at 0 here, and you put your right hand on that plane. So we're going to go around 0, 1, 8, 9 plane first. We could select any of the planes, but that's the plane I'm going to go with. So if you put your hand on the fist on the inside of the block, and your thumb should be pointing into the block. So if you put your right hand so that the thumb is pointing into the block, then your fingers will be in the order you have to go around the plane. So if I put my right hand there on that, you'll see if I start at 0, I don't have to start at 0, I can start at any points, but if I start at 0, it'll be 0, 1, 8, 9. So that gives me the first 4 points. So 0, 1, 8, 9. So then for the next 4, I basically, wherever I started, which is 0, I have to just move to the plane that's opposite that plane. So the plane that's opposite the 0, 1, 8, 9 plane is the 10, 11, 18, 19 plane. So move to that plane, and whatever point corresponds to point 0, that has to be the first, and then go in the same order. So keeping my hand that way, but now I move it to the opposite plane, and my thumb is pointing out of the domain. Then it's 10, 11, 18, 19. So 10, 11, 18, 19. So that's the first block. Then what I'm going to do is copy that and add another block, where the only difference is I'm going to change the points that this block uses. In fact, I'm going to copy that twice. One nice thing in blockMesh is can be difficult if you make a mistake in blockMesh. One of these points, you get some error and you're trying to figure out where the error is coming from. It can be useful to incrementally build your blockMesh state. And by that I mean is just check each block is fine and as you go. So to do that, what we're going to do is just leave that block defined, not define the other blocks. And then for this boundary, we're just going to comment all of that. We don't want the patches because these patches aren't correct for our geometry. So in C++, you can make a multi-line comment going / star, and then at the end of the section you want commented, which is just inside this parentheses, is a * /. So you can see it's all been colored red by Emacs in this case because it knows it's C++. Actually, the reason Emacs knows it's C++ is this line at the top. This is how you tell Emacs what type of code this is. So all the OpenFOAM files actually have the C++, so the editors like Emacs know how to color it. And so that's all commented. So boundary is still there, but it's just we are not defining any boundary patches. We've only one block, And that block doesn't use all the points, but blockMesh doesn't care if there's extra points that aren't used. So let's just save that, go over here and just run blockMesh. Let's just see what this looks like. So blockMesh runs fine. And it does give a warning saying found 6 undefined faces adding to a default patch. Because we didn't define any patches, it's saying, well, it's warning us, well, maybe you did something wrong, but it's going to make a patch and just add everything to this a patch called default patch for us. But that's fine for now. And so we'll go touchcase.foam so we can open it in PowerView. And let's refresh here and double click and open this up. So we'll wait for PowerView to open, press apply. So we'll get some errors because the boundary conditions in U and P aren't correct. That's fine, I can ignore those. If I just turn on the mesh and change the color, you can see, okay, we have a valid block to begin with. So it looks like cavity, but that's our first block. You can see we have default patches, which will just actually be the entire boundary will just be in this default patches. Okay, so our first block is fine. So now let's add our second block. So the second block, in this case, would be our block 1. So if we follow the same idea, we're going to start in the bottom left corner from this perspective, but we can start at any point. So we'll go 1, 2, 5, 8. That's our back plane. So right hand fist on the plane with your thumb pointing in, and then follow your fingers around. So 1, 2, 5, 8. So we go 1, 2, 5, 8. And then go to the front plane in the same order, starting from the corresponding point to 1. So it's 11, 12, 15, 18. So 11, 12, 15, 18. And now we can save that and run blockMesh and go back to PowerView, refresh, click, skip back. Now you can see we have another block added on over there. So we're slowly building up our mesh. I'm kind of ignoring the mesh density for now, but that's fine. It's useful to note what happens if I just say like the wrong point here. I make a mistake to see what it does. So instead of 0.15, if I put 0.14, that will be fine. You'll see in the box, then it'll just make a point going out over there. But we'll see later when we define our patches, if we define, say, 4, 5, 15, and instead of 14, we go 19, they don't make up a face of a block. So blockMesh will give you an error saying there's something wrong here. Okay, so our next two blocks will be, the right one will be 2, 3, 4, 5, and 12, 13, 14, 15. 12, 13, 14, 15. And on blockMesh, check it's happy, skip, fine. And then our last one will be 8, 5, 6, 7. So 8, 5, 6, 7, and 18, 15, 16, 17. 18, 15, 16, 17. Okay, we'll just check everything is okay here. Okay, so that's our blocks defined. Maybe we'll change the density just to be a bit more uniform. So let me check what I did on the slides, and I can just use the same thing. So I have 20 by 20, and then I have 10 because it's not as wide in the X direction, and then 30 because it's wider. So let's do that. So this block will only have 10 in the X direction, that's the middle bottom block, and 30 for the bottom right block because it's longer in that direction, and then just for consistency, the top block to be conformal has to have 10 in the X. So if I run blockMesh now, check, refresh, skip back time, you can see, okay, now it looks uniform. So just notice if I told this top block it had to have 20 cells, whereas this bottom had 10 cells in the X direction, blockMesh will give me an error because it can't connect those. The mesh has to be conformal. So we can just check that. If I set this to be 20 in the X, run blockMesh, so it'll give an error. So it says foam fatal error. So all errors in OpenFOAM will start with this foam fatal error. inconsistent number of faces between block pair 1 and 3. So it says the number of faces between block 1 and block 3 are not consistent. So block 1, remember we start with block 0. So this is block 0. This is block 1, block 2, block 3. So it's saying between block 1 and 3. So if we go back to here, that would be 1 and 3. So it's saying the number of faces in between those is not consistent. So we said there's 20 in the extraction here and 10 here. So you can see it actually tells you exactly where to look. And once you just understand the way OpenFOAM presents the errors. So let's just make this back to 10. So if you remember from the previous tutorial, we could stick in fancier grading here to have fine mesh near the walls, but we won't do that here. And we're not going to have any arcs either. So now the last thing we have to do is to define the boundary patches. So what we're going to do is I'm going to delete this, and I can leave front and back commented. So in the same way we make blocks 1 by 1, we can make patches 1 by 1, and then check blockMesh is happy with them, and that way you can easily find the errors as we're going. So we're going to have inlet 1. Inlet 1 is going to be this patch here. So let me see if I have it here in slides. So this is going to be inlet 1. Now we're going to have inlet 2 here, and then we're going to have an outlet on the far side, and then walls will be the other sides, and then front and back. So inlet 1, so if you remember from the previous tutorial, how we define them is we put our right hand with our thumb pointing out. So this is different from the blocks when we're pointing in at the start. So this is with your thumb pointing out, and then pick any point and then just follow your fingers around right hand rule. So if you pick point 0, it'll be 0, 10, 19, 9. We can start with 19 and go 19, 9, 0, at 10. Any one is fine. So 0, 10, 19, 9, I'll go with. So I'm going to go delete these ones, 0, 10, 19, 9. And then instead of it being a wall, it's going to be what's called a patch. So pretty much there's only maybe 3 or 4 different types if you use blockMesh to define the geometrical physical type. So a wall is a slip or it's a no slip wall typically. And the reason you call it a wall, it's just later on if you want to use wall functions, then this is the way it knows that the mesh where the walls are. So you don't apply a wall function on an inlet, for example, or an outlet. So inlets and outlets are patches, walls are called wall, and then empty is for the front and back. The only other one you might use is a symmetry plane. You're set to symmetry, and then there are some special coupled ones as well. So that's our inlet 1. We can save that. It's like patch. You run blockMesh, runs fine. Check power view, refresh. You can see it actually added a patch now. So the mesh doesn't change, but you can see if we turn on patch 1 or inlet 1, you can see it's in the correct place. And then default patches is every other boundary face. So you can see we basically have to add all of those to our own patch rather than letting them go into this default one. And so inlet 1, let's add inlet 2. Will be the same, but the 4 points will be different. So you can see just from this diagram, pick any point, right hand rule, thumb pointing out. So we can go 6, 7, 17, 16. So 6, 7, 17, 16. Keep going. We'll define the outlet. That would be a patch as well. We define your block. So the outlet over here, thumb pointing out, right hand. So that would be 3, 4, 14, 13. 3, 4, 14, 13. Just check blockMesh is happy. Yep, still happy, no mistakes. So now we have to define our walls and then our front and back. So the walls will be, I think I have a diagram here. So the walls are all of these orange things. So here's a wall, here's a wall. So 1 face, 2 face, 3, 4, 5, 6, 7. Okay, so I'm just going to copy and paste this because I'm not going to make you sit through me typing all this out. Let me see if I can remember how I pasted it. Oh, so if I right click, that pastes for me when I'm going from my Mac or Windows into here. Messed up the indentation, but that doesn't matter. There are settings in Emacs so you can fix indentation and things like that. That's fine. Let's just check it's happy with that. Very good. And then the last thing then is the front and back, which you can see there's loads of as well. So I'm just going to cheat here and copy them out from here. So I click over here and I click. I'll delete this. The indentation doesn't matter here, but I'll make it a bit better. Save that, run blockMesh, and hopefully that should be everything we need for our mesh. So we go back to Power View, refresh, go back to the first time step, and default patches should be empty now. So if we go to our patches, so you can see it also allows you to load groups. So groups are all the walls. So in this case, all the walls are actually just in a patch called walls. So it doesn't matter. But if you had like multiple different wall patches, you could just load them quickly like that. So there are actual walls. If we turn on our outlet, outlet's over there. We turn on our inlet 2, turn on our inlet 1, and turn on our walls again. So there you go. So if I click up here, turn everything on and off, and just turn my internal mesh on, and that's our mesh. Okay, great. So we're pretty much ready to go. One thing just to show you errors. So if I mess with one of these patches, so say the outlet patch, instead of 3, 14, 15, 13, if I put like 133, so there is no point 133, and I run blockMesh. So let's say point label 123 is out of the range of 0 to 19. I've only points 0 to 19 on patch outlet face 0. So patch outlet is this one, and face 0, it has one face, so face 0 is the first one. So you can see the error clearly tells you where to look. So instead of 13, maybe I'll set that to 18. So there is no face that has those combination of points. So if I run blockMesh, it gives a different type of error. So it says face 0 in patch 2. So let's see what face 0 in patch 2. So the patches here, this is patch 0, patch 1, patch 2. So it's telling us about the outlet, and it says face 0. So face 0 is this one, it's the first one. So it says there's something wrong with this face. And it says it does not have neighbor cell face 3, 4, 14. So it's basically saying that there is no face that has those combinations. So if I just reset that back to 13, blockMesh, and we're good to go. So before running the case, we just need to update our boundary conditions, and we know Power View kept complaining about them. So I'll open up U. So instead of a moving wall, I'm just going to call this inlet 1, and I can leave the velocity of 1 meter per second in the X direction. I'll copy that, inlet 2, and that's going to be velocity coming in the minus y, so let's say minus 5. And we've fixed walls. I think we just call that walls, and that's going to be no slip. I'm going to copy that, and then the last thing is I have to add an outlet. So what boundary condition do we have for an outlet? Well, typically in an outlet we specify the pressure. So we don't specify the pressure at an inlet or at walls. We use the zero gradient, which basically means that we assume the variation away from the inlet or the wall is constant for pressure. But at the outlet, we're going to specify the value of pressure. So that means for the velocity, we won't specify the outlet at the velocity. We'll let that be calculated, but we'll set the gradient of velocity away from the wall perpendicular from the outlet to be 0. So we're basically assuming that there isn't much change if you plot it from the outlet going into the domain. We're going to assume that the velocity is not changing much as it's going out through the outlet. Then I'm going to go Control XF, and open up pressure and do update the boundary conditions for pressure. So we're going to inlet 1 is 0 gradient for pressure. Inlet 2 is 0 gradient for pressure. The walls are 0 gradient, and then we're going to specify the value at the outlet. Our outlets, and to specify the value in OpenFOAM, you go fixed value. You're fixing the value, and then you go value. And because there's multiple faces, you could actually give the value at every face. So if you go uniform, it means use the same value. And this is a scalar pressure. So we're just going to set 0 gauge pressure. The order in this file doesn't matter. So I can move outlet to the bottom, it doesn't matter. It's just the order in the blockMesh stick, and the actual mesh actually means something. But here when it's looking for a boundary condition for inlet 2, it just looks up this list and it just goes down through and finds whichever one's there. So it doesn't matter the order. Okay, and let's check. We're going to leave the transport properties, the viscosity will be the same. But we're going to change the time step. I think the cells might be a bit smaller, so let's try make it much smaller. So the end time maybe 1 e to the minus 4, and the time step 1 e to the minus 5, and right interval 1, which means based on the right control of the time step means right every time step. So I'll have 1 e to the minus 5, 2 e to the minus 5, 3, etc. Save that, and let's run OpenFOAM, see if it's happy. Runs through. Okay, so the current number is less than 1, so that's fine. So our mesh is right size. So we had increased the velocity, so that's why we had to increase or decrease the time step. So you may well try and error, just run a few time steps and check the current number. So if we refresh now, we should have multiple time steps up here. So we have 10 of them. If we go to our velocity, and maybe I'll set this to 2d and minus z. And if I skip, you'll see this flow developing. So it's initially maybe there's some oscillations, and then they tend to die down. So I could probably, if I run that a little bit longer, so maybe over here, I can now change open the control dict, maybe multiply it again by 5 on solver again, and go back, power view, refresh. So play further. Yeah, so you can see it's pretty much settled down now. So so it reaches steady state pretty quickly because of the high velocities. So of course you can stick in your streamlines and all of that stuff, and you can see what the effect of understand the flow better. Also, you can notice the magnitude of the velocity coming in here. So we could look at the x and the y directions. Z will be 0. But you can see we have a uniform incoming velocity. We didn't specify a per parabolic velocity. So you can see here actually the parabolic velocity naturally develops on its own, and it actually does the same here as well, but you could specify parabolic velocity. But that's the end of this tutorial.